Hey guys, hope you're well. Hope you're staying safe. Welcome to another session of computer architecture. In today's session, we're going to be looking at the 2016 past test paper. Now, just to reiterate that as far as your module content is concerned, remember your test is going to be covering chapters 2 to 8. So just take that into consideration there. And I think we've mentioned this in sessions before where we said that as far as the type of questioning is concerned, you will have a couple of multiple choice questions thrown into the foray there. You will also get match columns. You will also get your missing words in some instances, and then obviously your long questions, which are the scenario based questions associated with your module content there. So if you've got the 2016 paper, naturally it's going to be 1 hour as far as completion is concerned, and then obviously mark allocation there is a total of 60 marks. And then as far as that whole paper is concerned, remember, as we've mentioned before, your actual pass mark is going to be 50%. So question number one constitutes 20 marks, and you're sitting with 10 questions there, and obviously that's 2 marks apiece, and it's multiple choice. And I think if you've looked through this paper, obviously I think the last time I posted content, I'd asked you to try and look at this paper on your own, obviously mimicking an exam or test sitting, so that at least when we look at it, you can gauge as far as understanding module material is concerned, and it obviously makes it a lot easier for you to obviously get an understanding of where you're at and what it is that you probably might need assistance with in terms of you understanding fully what's happening as far as module content would go. So you've got a multiple choice set up for question number one there. And if you look at 1.1, they've asked, so with this particular question, you're actually looking at chapter number 2, which is all to do with operational procedures and obviously the traits of the PC tech. And in this particular instance, you've got a specific individual that has lost a file, and they've called to ask where they could typically find this file, and you've got a list of answers that are there, and obviously the most appropriate answer for us there would be B, because naturally when you're looking at the whole concept of assisting anyone within your tech spaces, you obviously need to make sure that you don't use jargon, and at the same time you are as polite as necessary. But remember, like we've mentioned before, in some instances you obviously need to be assertive as well, but that doesn't mean that you need to be rude or curt in your distinctive responses there. So 1.1 would be a B, and I think, again, if you've looked at this paper, you'll discover that I think the revision questions that we had, I think we had those 2 papers that I've uploaded. You might find that most of these questions arguably are one and the same, and naturally, again, the whole concept was just to make sure that you understand the type of questioning that is there. So these are more or less guidelines, so you understand specifically what is happening as far as assessment would go. So 1.1 would be B there, and then number 1.2 asks you what sort of connector does a typical network interface card have. So your NIC obviously deals with what they call registered jacks, and you've got different pins, or more or less different connectors that are there. So you've got an RJ6 connector, you've got RJ11, RJ9 in some instances, and then you've got RJ45. So naturally, when you're looking at your generic networks, RJ45 would be your default go-to there. RJ6, 9, and 11 arguably incorporated within the telephone space, or when you're looking at a basic telephone connection as far as the whole telecommunication space is concerned. So 1.2 there would be D there. So it's RJ45, also known as registered jack 45. And then if you look at question number 3, 1.3, it asks you which CPU feature enables a microprocessor to support running multiple operating systems at the same time. Now remember, I think we mentioned this when we were having our face-to-face sessions, and we had mentioned the whole concept of the need to probably run multiple OSs just to either understand specifically what's happening with these OSs, in some instances also checking some of the glitches these OSs might have, and also looking at probably testing certain updates before you actually roll them out to the actual machine itself. So in essence, if you're looking at it from a basic perspective, this would naturally mean you'll need to arguably load these multiple operating systems on different machines, and in some instances it might not be economical for you to do that. So there was an architecture known as virtualization that was designed that arguably enabled you to run multiple operating systems on a distinctive computing machine or computing mechanism there. So naturally, what we're typically saying is that running a computer system within another computer system. But remember, this was only possible, or this naturally is only possible if you've got the appropriate processor that can accommodate for that. And that particular feature is obviously known as virtualization, like I was saying earlier on. So 1.3 would naturally be virtualization support there. All right. Remember, clock multiplying is a different thing altogether, because you're looking at that typically looks at the whole concept of overclocking. Caching is discussing the whole concept of using your SRAM for that fluid execution of instruction sets. And then you've got pipelining, obviously works hand in hand as far as the whole concept of making sure that instructions are executed in a smooth fashion within your environment, just to avoid bottlenecks. And then you've got 1.4 there. Now you've got a specific individual. They've added 1 gig. So I think I've mentioned this before. What's imperative, especially when you're looking at the whole concept of answering some of these questions, you need to identify certain content that is not relevant, that doesn't change the answer or doesn't affect the answer, or doesn't more or less you're looking at a certain content that don't influence the outcome. All right. So in certain instances, so if you look at a question like this, you've got a 1 gig 240 pin DIMM that's running on a specific machine there, to put it up to 2 gigs of RAM. And then they mentioned that you're running an Intel Core 2 Duo 3 gigahertz processor, and you've got three slots that are there as far as the actual board is concerned. So some of that content is not relevant, because if you look at the actual question, when this particular individual boots up his machine or runs RAM count, it's still sitting at 1 gig of RAM. So naturally, what that means is you're typically in an environment when, if they've plugged in something, then obviously it means they've got enough space for that. So the whole concept of having three slots that are available on the board, or three slots that the board accommodates, is arguably irrelevant. So make sure you understand, try and look at a way of looking at the important content that is relevant in terms of enabling you to troubleshoot a specific scenario appropriately. So if you look at this particular question, we're saying this particular individual has plugged in a RAM module, but once they've done that, they run RAM count, or they boot up their machine, and it's still sitting at 1 gig of RAM. And then what we've got there is, you've got failed to seed RAM appropriately as A, you've got B, DDR SD RAM in DDR2 slot. Remember, when you're looking at RAM, like we mentioned before, you already know that the DDRs are not forward as well as backward compatible. That is out completely. The CPU cannot handle that much RAM. Naturally, now you can then look at the whole concept of, if it's an Intel Core 2 Duo processor that's running at 3 gigahertz, obviously that's quite, or that was quite powerful in back in the day. But that obviously means that you're running it at a 64-bit architecture. So naturally, it means that it can accommodate for more than 4 gigs of RAM now, if you want to look at it from a very specific perspective. And then you've got the motherboard that can only handle one slot at a time. Obviously, that doesn't make much sense. So the appropriate answer for 1.4 is going to be A, which means that this particular individual did not seat the RAM module appropriately on the actual board itself, because every other answer that you find there doesn't make much sense for us. as far as answers would go. And then 1.5, you've got now the boot sequence. So we've mentioned this before when we're discussing the whole concept of BIOS specifically, and understanding what is happening in terms of what takes place when the machine is actually switched on or booted. And remember, the first thing that you need to take into consideration, like I've always said, try and avoid cramming, but understand the process. So obviously, if you look at it from a generic perspective, power needs to be there. Once power is okayed or is deduced, then naturally you've got to check for the other important components that are incorporated within your machine itself. So the most important component would be your CPU. Like we said before, arguably the brain of the machine. Bit of an overstatement, but like we've been singing before, it gives you an idea of what that particular machine, device does for you, or component does for you. Then after that, you need to check for the other components that enable the machine to run appropriately. Because now, at the back of your mind, you now need to be thinking about that whole input, process, output, and eventually storage platform that we've mentioned before, in terms of you being able to actually label a specific electronic machine or electronic component as an actual computer system. Then after that, naturally, you need to have a mechanism that enables you to find where the actual operating system is sitting. And then once that is gotten, your OS typically loads. So the appropriate answer for us there, as far as 1.5 is concerned, is going to be your D. So it's going to be the power good wire. That's the one that's responsible for typically waking up the CPU, most important component. Then you go to post your power on self test, which is the third stage. That then checks for the other components. So your hard drive, your RAM, and naturally your graphics. And then you've got the bootloader, which is responsible for checking where the actual operating system is sitting. And naturally, remember, you can boot from the internal hard drive, you can boot from an external hard drive, you can boot from an optical drive, you can also boot from the network. Once that stage has been successfully completed, then naturally your operating system starts loading, or you start to see the logo there. So 1.5 is D. And then 1.6, which variation of PCI was specifically designed for laptops? So that one would be mini PCI. Remember, your peripheral component interconnect bus or connection mechanisms were initially designed to expand the whole usage of the machine. And naturally, the one that is miniaturized, or the one that was designed for your laptop devices, was your mini PCI. So 1.6 would be C. And then 1.7, feature of ATX systems. Remember when we were discussing, so this is now looking at the power supply chapter. And in this particular instance, we're looking at the whole concept of actually, even when if you want to look at it, when you look just discussing boards in general, the actual feature that enables the whole concept of you being able to shut down the operating system without without touching your power button there, is what they call soft power. All right, so that's an ATX configuration there. So more often than not, associated with ATX power supply units there. So your answer for 1.7 would be D. And then 1.8, so you've got a troubleshoot theory. Remember, you've got those 6 steps that are there. And in this particular question, they're now asking, what is the first thing that you should do when you arrive to work at a computer system? So you want to work on a machine. What's the first thing that you typically need to do? And then so with this one, you obviously also need to make sure that you understand specifically what the question is asking of you here. So it says, what is the first thing you should do when you arrive to work on a computer system? All right, so if you want to work on a machine, is so you've got to identify the problem, you've got ask the user who broke the machine, start working on the machine immediately, back up critical data, and then none of the above. So remember, you want to work according to the this is according to the troubleshoot theory. All right, so technically what you want to do here is the first thing that you want to do when you arrive to work on a given computer system. You need to identify what the problem is. Others might want to now argue, okay, what about backing up critical data? Because we've mentioned this before, but remember, you can't start backing up critical data if technically we're now saying without understanding what the actual problem is. You get to know what the problem is before you start working on it, or before you start fixing the problem. That's when you start backing up critical data there. So the first thing that you want to look at as far as 1.8 is concerned is then identify what the problem is, and then naturally after that is done, you need to start backing up your data, because remember, that's part and parcel of you now establishing a theory of probable cause. And then so that's 1.8 would be A. And then 1.9, again, troubleshoot theory. You've successfully repaired the machine. Remember, you need to make sure that every time that you've concluded any any troubleshooting, you then need to make sure you document your distinctive findings there. So 1.9 would be C. And then lastly, for the multiple choice for question number 1 there is, again, according to the troubleshoot theory, you've ascertained what the computer's problem is, you've backed up the critical data. What should you do? And if you checked appropriately, actually 1.10 gives you a heads up in terms of with the answer for 1.8 as well. So I mean, look out for those kind of things when you're answering your test there, or when you're doing any kind of assessment anyway. So according to troubleshoot theory, what should you do after you've backed up the critical data? Then obviously you now need to establish what the actual issue is. So establish a theory of probable cause before you actually start fixing the machine. So I think the other takeout from such questions is, the moment they already tell you that you've got to troubleshoot you according to the troubleshoot theory, that's what you need to stick to. Because remember, with the troubleshoot theory, you've got those 6 steps. You need to know those steps. You need to understand why they're there and how they fall within each other. And then obviously that makes it easier for you to then answer such questions. But I think my advice when it comes to such questions, the moment they tell you according to this, then you know you need to stick to the actual steps or stages associated with that theory there. So that's that for question number 1. And then if you're looking at question number 2 now, again, another 20-mark question. But with this one, you've got scenario-based questions and a couple of definitions as well that you need to take into consideration. So they've given you an image and they've asked you to identify what is the tool and explain how it's useful as far as troubleshooting is concerned. So that particular tool that you find in 2.1 is your anti-static wristband. And remember, the main purpose for such material, the main purpose of such a tool, is to circumvent ESD. Or technically, you're looking at the whole concept of trying to safeguard against electrostatic discharge there. So it's useful in the sense that it safeguards against ESD. And remember, ESD is quite detrimental because it completely damages your components. So you want to make sure that when you work on a computer system, you try and avoid that. And then with 2.2, again, list 5 peripherals that use a USB connection. Remember, your USB port, universal serial bus port, was initially designed to more or less to make the whole concept of connectivity a lot easier when it comes to physical connections as far as peripheral components are concerned. Remember, we've mentioned this before, any peripheral device is something that complements the whole computing system there. So anything extra in terms of your keyboards, your mice, your not monitors per se, but your printers, your scanners, all those complement or complete the whole concept of the computer system or your system unit there. So you've got a multitude of devices. So it was designed to avail for ease of access and to limit the whole concept of having to have dedicated ports that were designed for specific devices. So that's where the universality comes into the foray there. So you've got 5. All you have to do is just list with this particular question. So you've got, like I've mentioned before, you've got your keyboard, you've got your mouse, you've got your printer, you've got your scanner. You can even discuss external storage components like your external hard drive. You can also even discuss your speakers as well, because you've got some speakers that can, even headsets that can plug into a USB port there. So all you have to do was just mention any 5 of those as far as that particular question is concerned. And then 2.3 now is installing, so it's about CPU. So they've asked you here, installing a CPU, CPU fan and RAM before the motherboard is installed in the case, can assist in different ways. So explain how this helps the tech. So this particular question, I think you've already experienced this when you were completing your exercise in class. The last time we obviously had sessions there. And one of the advantages, if you want to look at it from a different perspective, of plugging in all those devices, especially your CPU fan, your fan, and your RAM, is it makes it easier in terms of access, because if you plug in the board in your specific case before you plug in these devices, as far as reaching is concerned, makes it difficult. And obviously the more difficult it becomes, the more prone you are to damaged components, because remember, your board is delicate. And the other thing that you also want to discuss is the fact that you also safeguard against flexing. Remember, your flexing is that bending of your motherboard inadvertently. And if you uh, are going to be incorporating this content, well, we're trying to plug in these devices or plugging these components while your board is inside, you could flex the board in terms of bending it. That's also something that you're trying to safeguard against. So the whole concept is just easier, and you're trying to safeguard against damage of the actual board itself. So it just makes it a lot easier for you when you plug in, and you avoid the whole concept of, or the whole issue of you damaging the actual motherboard per se there. So that's at 2.3. And then when you look at 2.4 now, again, you've got a troubleshoot theory. So I think this paper was a bit um, simple in the fact that most of the questions arguably repetitive in some instances, but at least you've been given a heads up in terms of some of the stages associated with the troubleshoot theory, especially if you go back to your multiple choice questions there. So you've got those 6 steps that I mentioned before. So in this particular question, they've given you the first one, and they're now asking you what the subsequent 5 steps are. So the first one is to identify the problem. Now, where your marks start coming in is from the second to the sixth. So the second one now would be establish a theory of probable cause. The third would be to test that theory. The fourth one is to develop a plan of action. And then once you've done that, the fifth would be to verify full system functionality. And then once you've done that, then you need to then document your findings. So the last one will be documenting your findings there. So those are the 6 steps there. They've asked you for the subsequent 5. So that's question number 2. And then if you look at question number 3, again, another 20 marks for you there. And with this particular question now, they're looking at explain how cache, and remember, cache is also known as SRAM, or static random access memory, that can, how can it support CPU pipelining. So if you remember the chapter where we're looking at, I think this was chapter number 4, to deal with it was dealing with microprocessors, and one of the specific architectures that were developed, or that explained how the specific CPU functioned, was pipelining. And remember, with a pipeline, you've got 4 distinctive stages that to enable you to understand how an actual instruction is executed. So the first stage is to fetch, which is to collect the instruction through your EDBs there, and then after you've collected the instruction from the EDB using the EDB. Remember, your EDB is your external data bus. And then the second one is to decode the instruction. So this is understanding what the instruction is. Once that instruction is understood, the third stage is to execute that instruction and actual undertaking of the instruction. And then naturally the results of that is written back to the external data bus. So your write back would be your fourth stage. So when you look at cache now, because when we were discussing the CPU, we mentioned that your cache or your SRAM is the fastest memory that is associated with your computing mechanism. Why? Because it typically functions within the same confines of your central processing unit, or tries to mimic that distinctive speed. And it's designed specifically to more or less reduce what they call wait states. And remember, wait state is more or less like a bottleneck. So it reduces wait states by preloading instructions or preloading um, frequently executed or frequently acted upon instructions. And in this particular instance, it means that it also keeps copies of these instructions, so that the next time that same instruction is called upon, naturally the execution is a lot faster. So think of caching within the same confines of browsing. I think we mentioned this before in class, that we said that when you're looking at maybe browsing we're looking at your browser as an argument. if if you've got a set of sites that you access on a frequent basis, those sites are cached, so that the next time that you access the same site, it loads a lot faster, because it's arguably already preloaded in that particular environment there. So that's the same thing when you look at your SRAM or your cache. So it avoids the bottlenecks, looks at a systematic execution of these instructions, and how does it do this by preloading these instructions. So technically, it's all to do with reducing wait states or reducing your um, bottlenecks. All right. And then if you look at question number 3.2 now, it says list any four types of errors associated with RAM. Now remember, RAM is that um, primary memory that is necessary, especially for execution of instructions. Why? Because these instructions are held somewhere first, which is in this particular RAM component, before they naturally collected and acted upon. So you've got distinctive types of errors that would point directly to RAM issues. And you've got four that they've asked of. So the first one is your parity errors. Now remember, we mentioned that parity was an earlier mechanism or architecture that was developed to check for the correctness of instruction sets that were stored in your RAM there. You've got the odd and even parity configurations that we've discussed before. So you've got parity. And remember, what was developed to more or less alleviate some of the issues associated with parity was ECC, or error correction code. So that's another type of error that you can get, which is the second one. The third one is system lockups. So your computer system freezing, your computer system being non-responsive, could actually indicate a RAM problem there. And then lastly, the fourth one is your page faults. And these ones, remember, with anything to do with the page, when you're discussing memory, or we're discussing RAM, has to do with virtual memory. That space that is stored, as far as your specific hard drive is concerned, to aid or assist physical RAM that is installed. So you've got parity, which is the first one, ECC errors, which is the second one, system lockups, which is the third one, and then the last one would be your page faults. Number 3.3, as far as question number 3 is concerned, describe how ROM, BIOS, CMOS are related. List at least 3 facts in point 4. So this one, remember, ROM is associated with firmware, and naturally, when you're discussing firmware is another term for BIOS, or basic input output services or system. So ROM is a storage platform for the BIOS, which is your firmware, and then obviously you've got CMOS, which helps read the BIOS. So technically, the CMOS's main purpose is to assist in the whole concept, or more or less enables you to read what is associated with, or what is incorporated within BIOS. So your BIOS would be the services or the programs, and then your CMOS deals with system parameters or device parameters, if you want to look at it from a different perspective. So CMOS enables you to read what is in BIOS, and then obviously BIOS is stored on your ROM, which is your storage platform. So if you want to look at it in point form, ROM is read-only memory, which is your storage for your BIOS, which is your firmware. Your BIOS is services that enable, or the core services that dictate how the machine functions, and then your CMOS on the other hand enables content in BIOS to be read, and your CMOS actually is all associated with or stores device parameters. And then 3.4 there is now looking at identifying certain components that are associated with your computer system. And the first one there is your CPU, well, not your CPU rather, but your PSU fan. So that's your power supply unit fan. That's so you've got one marker piece just for identification there. 3.4.2 is going to be your motherboard connector. 24 pin in essence, and then you've got so motherboard power connector, that's 3.4.2. 3.4.3 now is going to be your SATA power connector. Normally this is a 15 pin connection, and then the last penultimate one is 3.4.4, which is your PCIe power connector, 6-pin connector. So that's PCI Express, and then the last one is going to be your digital multimeter there, which is 3.4.5. So that's your paper, the 60 marks associated with that specific assessment. I hope you got most, if not all, of the answers correct there in your own self-assessment. I will be posting again, reviewing the 2017 one, I think in the next 24 again to 48 hours, but I'll give you a heads up via Learn. If there are any questions, as usual, please pop me a mail and let me know where you might need further clarity, or where you might need assistance. If you've got different opinions, especially with some of these other questions, also give me a shout, and then we can engage ourselves accordingly as far as the online platform is concerned. All right, so there it is, guys. Thanks for tuning in. Again, please stay safe, stay positive, keep smiling. We will see you in the next session there. Cheers.